All right, final exam review. We did a lot this semester. And you heard me cough a lot towards the end of the semester. Sorry about that. But the beginning of the semester is one of the harder topics to understand because when we think about power, we think about watts, right? Doing real work. But we had to get into more depth or more discussion about power, mainly because you have AC circuit analysis, which is using averages, right? Over one cycle, essentially, what is happening to your system. And so in the case of capacitors and inductors, ideal capacitors and inductors don't consume any real power, but they store energy and then they put it back into the system. And so what we had to do was expand the concept of power from instantaneous power to average power. And when we saw we had average power, what was the power delivered to a load over one complete cycle, we could define that as watts. The problem is that that's an incomplete picture because the current magnitude and the voltage magnitude, that current going out to your system does not account for that power. There's more current magnitude in there than what is provided or what is indicated by the real power delivered to the load. So what ends up happening is you get skewed results. And so that's when we had to add in that additional term called the total power. And the total power includes the real power plus any of that power that is sent out for half the cycle and then absorbed back into the system, because that does affect the magnitude of the current. So we started to introduce total power, reactive or imaginary power, and real power. And what that allowed us to do was to build a power triangle, because the real power is always in line with the real axis, and the imaginary power is always in line with the y-axis or the imaginary axis. And so the vector S is just the combination of those, the vector addition of those two. And then we had to define even one more term, which is very useful, which is describing what proportion of total power is real power. And a term that we came up with was power factor, right? So the power factor is just the ratio of the total of the real power to the total power. And once we had one term, PSQ, and we knew what the power factor is, it's just a right triangle, so we can go ahead and solve for any of those terms. So being able to talk about the concept of power and a power factor is how we talk about things in industry and makes things really, really useful for us. The other kind of addition that we had to have for power factor is sometimes the power factor is lagging or leading, which is sort of unfortunate because power factor doesn't lead or lag, but we call a leading or lagging power factor, which actually translates to the current. Is the current leading or lagging the voltage for that particular phase? Okay, so that's where we had to get more in the concept of average power, power factor, and whether that power factor is leading or lagging. Hopefully by this point, you feel pretty comfortable and using the terminology so you understand what leading and lagging is. Is it a current? Is it a voltage? No, it's always the current that leads or lags. And a nice thing that really helped us when analyzing systems is developing phasor diagrams. And phasor diagrams only apply to those elements that are phasors. What is a phasor? Voltage and a current. Phasor has a sinusoidally varying component. So if you were to look at any instant in time, that voltage and current are changing. Power, because its average power, isn't changing. And reactances or resistances are fixed. Those aren't changing as well. So power, whether it's real, reactive, or total, is not a phasor. Same thing for impedances. Those aren't phasors. But voltages and currents are, in fact, phasors. And when you compare phasor diagrams or look at phasor diagrams, you can get a lot of information when you look at voltage magnitudes and angles, current magnitudes and angles, and you can tell a lot about a system. Okay? And once we got into phasor diagrams, because those are just vectors, at that point, we're just adding or subtracting as necessary, multiplying, dividing. That's just complex math, being able to do that. If you were to go ahead and analyze a circuit with inductors, capacitors, and resistors, you'd have to write differential equations to solve those, right? Because L dIdt or C dV/dt are the actual equations in the time domain to solve for voltages and currents. Problem is, We don't want to do differential equations. It's a lot of work for not a lot of bang for our buck, particularly when we're looking at an average or kind of a system over a longer period of time frame. So we do everything in steady state AC circuit analysis, which converts those inductors and capacitors to reactances. And because they can introduce a phase shift, we have to include plus or minus J terms as necessary. And so we just added those terms and we got the results that we would need there. Inductors, it's 2 pi FL. Capacitors is 1 over 2 pi FC. Capacitors have a negative J to account for the phase shift that it introduced, and inductors do a positive J to account for their phase shift. We can't really do a machines course or an electromechanical energy course without having some magnetics, because that's the go-between, right? That's the magnetic circuits are how we transfer between different domains, if you will. And so we spent a little bit of time talking about magnetics. And what I mean by magnetics are generating and utilizing magnetic fields. So we talked about how magnetic circuits are very similar to electric circuits in that you had a voltage and a current and a resistance, but we called it MMF, phi for flux, and reluctance. Those are the similar terms. Where we got very different, though, from electric circuits is magnetic circuits have to be operated at much higher levels of saturation. And they can be because you're not really dissipating any energy, right? Because it's all magnetic. So you're not generating lots of heat. You're not going to burn up a magnetic core like you would a piece of copper if you ran it under very high current densities. So you can push these really hard, and you need to, because copper has, something like 2 million times, 3 million times better conductivity than air. But magnetic circuits, the best material around is maybe 100,000 times better conductor. So we would need so much material to get a much better magnetic conductor. It's not worth it, particularly because we don't get the same line losses. And so we had to operate with the concept of saturation. And so the only way we can deal with saturation is just like we did by doing circuit analysis with electronics. We would have a small operating point and pick that point on the curve. So you have to look at curves and say, here's the equivalent of my beta, if you will, right? If you all remember from BJTs, you had the concept of beta, and that was based on the biasing current. Same thing over here. The amount of excitation current that I'm driving through a magnetic circuit is going to affect the degree of saturation. And that really showed up when we started looking at generation, and we looked at calculating synchronous, saturated or unsaturated reactances for the synchronous impedances. That's where that stuff kind of came about. So we didn't get too much into magnetic circuits because that's really not the purpose of this class. We want a little bit of a background to understand magnetic circuits because we are using them extensively, but we don't need to be experts in magnetic circuits. If you want to become an expert in magnetics, then you can take, at least at UMaine, is ECE321. I don't think mechanical engineering or any other disciplines, maybe physics probably has a bunch of magnetic circuits, but most of the other disciplines don't really get too involved with magnetics. So if you really want to get into magnetics, there are a bunch of EMAGS courses. Those are some of the fundamental classes. They can be very challenging because there's a ton of vector calculus that needs to be done to make that work. And that's the other reason why we don't delve too much into it, because to really understand magnetics, you really need a pretty good understanding of vector calculus, gradients and curls, because dimensions and locations make a big deal. We won't do that. So we moved on to three-phase circuits. And three-phase circuits, we learned, are super duper useful for a couple reasons. First off, you can use twice the amount of power, move twice the amount of power for the same amount of copper. And you also get beautiful rotating magnetic fields. When you have a three-phase balanced system and you run that through some sort of device, a coil of wire, for example, that can create a magnetic field. And if you orient things properly, you get a really nice 100 or 100, a magnetic field that rotates around really well. So primary reason is we did things from a cost savings perspective, lost copper, but a benefit of that is we have these beautiful magnetic fields. And in a Y connection, you have 3 wires coming out, same as in a delta connection. The difference in a Y connection is you also have a neutral that you oftentimes don't run out unless you have a bunch of loads that are single phase. off of whatever that, Y system is. You oftentimes don't need the Y because you're not going to run it. Again, we want a balanced system, so running a Y connected load makes the system unbalanced. So unless you're dealing like with some lighting load where it just doesn't make sense to run a 3-phase wire to a light because it's not practical, then we wouldn't run the neutral. So motors, transformers, all that stuff, you don't run neutrals out because those loads don't need it. It's a zero reference point. But this summary table here provides some detail about the difference between a Y and a delta. You can look at magnitudes of voltages and currents, and you can see the differences between the Y and the delta. The voltages are different. Magnitudes of the voltages are different for those, but in, let me back up. Phase voltages and line voltages are different in a Y, but the same in a delta, and the opposite for the currents. In a Y, phase voltages, phase currents are the same as line currents, but in a delta, they are not the same. And you can see how you can do those calculations. We also understood that there's ABC sequence, which those three phasors, VA, VB, VC, or IA, IB, IC, are always going to be 120 degrees apart. But the rotation of those phasors, which one do you see first? It's always phase A. And then do you see B or C next? That will make more sense if you take the follow-on class and why we switch them, because sometimes we do another term which is called positive sequence rotation or negative sequence rotation. But when you do a different sequence, you can see that I have my line and phase voltage, my line voltages, my phase voltages may not be the same. Not only is there a magnitude difference, but there's a phase shift as well, a 30-degree phase shift between the two. Or if the currents aren't the same, like in a delta, you can see how the magnitudes are going to be different, but also we're going to have a phase shift associated with that. And then the last thing we did when we talked about three-phase systems is all the circuit analysis is the same. In fact, we really look at single-phase circuit analysis because one phase has the same magnitude and the other phases are just offset by 120 degrees. So why not just analyze the systems by single-phase approach? Much, 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 much easier to do the calculations. We have to twist it a little bit because now we need to add in the fact that if I'm doing single-phase analysis, sometimes I need to multiply that calculation I need by 3 or the square root of 3. It just depends on what I'm calculating. If you remember on our last exam, when we were talking about what are the rotor copper losses or stator copper losses, if you just did I squared R, that's one phase of I squared R losses. I've got 3 phases, so you're going to multiply as required by 3. So when you go to 3-phase, just keep that in the back of your mind. If I'm looking at resistors, remember I have 3 resistors, and I have to include all the losses, so I would multiply by 3. The only time you're ever going to see square root of 3 multiply something that is not a phasor, because I can look at my table and all I see is square root of 3 here, those are phasors. The only time I see square root of 3 here is in this calculation for S, for the total S for a 3-phase system. And that's only because I've snuck in not phase voltages, but line voltages and line currents. Okay, so I made a substitution in to do that. And this equation is the easiest equation to use because most of the time you're going to be given line quantities when you do your calculation. So if you use that one and you use the line quantities, it makes things quite a bit easier. When you calculate power, power is just vectorially added. So if you calculate the power for one load or load and another load, you just sum them together algebraically. Super, super easy to add. And so that's what we do when we do calculation for loads in a building or on a panel. We figure out not what the currents are, because the currents go in all different directions, but we figure out what the power consumed by each load is, then we add them up. Makes the calculation really easy. Now we start to move on to transformers. So a huge, huge important device for us, because that's how we reduce dramatically line losses in the system. So we can go ahead. Terribly sorry. I was trying not to have to clear my throat so much, but I guess it doesn't work. But transformers, all their purpose in life is to reflect voltages from primary to secondary and conversely currents. Transformers are considered constant power devices, very, very, very efficient. but all the power coming in has to come in through the primary winding and then delivered onto the secondary winding with maybe a few losses in the transformer. And so because that's a constant power device, if I step the voltage down through the transformer, I had better step the current up. So we can discuss the concept of the turns ratio, which is based on the number of primary turns divided by the secondary turns. But nobody does that because when you buy a transformer, you don't know primary and secondary turns. You know voltage ratings, voltage rating on the primary and voltage rating on the secondary. So you can calculate the turns ratio based on those voltage ratings. And you can do the same thing for current, but current usually isn't specified on a transformer. Usually it's written as voltage ratings and a power rating. And that's how you can back calculate what your current is. Okay. When you have impedances on one side of a transformer and you're trying to get the equivalent of that impedance on the other side of the transformer, you need to reflect that by either the turns ratio squared multiplication or division by the turns ratio squared. And that's how you can move things along. It's a good thing because as we talked about, our house maybe looks like a 10 ohm resistor, but from the utility perspective, we look like a 7,000 ohm resistor. So we're not drawing lots and lots of current at whatever the utility voltage is. So it makes our system, again, very efficient, and we can deliver all the power we need. We did the equivalent circuit of a transformer. So we don't deriving that here because we're just going through and doing a review. But here is our transformer equivalent. And we got a lot of stuff to calculate. And how do we calculate that? With the open and short circuit tests. This is just a summary of the process to solve for those parameters and what you solve for. And I even label them as to what these individual parameters are. You can see the parameter is make sure you apply the rated parameter. In the open circuit test, that's V open circuit. In the short circuit, it's I short circuit. Then you measure the resulting parameter. You've applied a voltage or a current. Now you got to figure out what is the other voltage that is being dictated because I'm applying rated value. In this case, it's either voltage or current, depending on which test you're doing. And you can see I've labeled them, right? ISC, VSC, or IOC, VOC. Then we have to measure the input power because we don't really have a device that can calculate the phase angle between the voltage and the current, but we can measure the input power. We can use devices that do that. We have to measure both powers here. And once we do that, we can use our trig identities and our power triangle to calculate the angle between the voltages and the current. Recognizing that that current is going to be lagging, right? It's going to be lagging because this is an inductive circuit. I look at the equivalent circuit. I don't see any capacitors there. So we know in an inductive circuit, Eli the ice says that the current is going to lag the voltage. So we're always going to end up with a positive angle because when you take a voltage at an angle of 0 and divide it by an impedance that has a positive angle, you're going to get a current that lags the voltage. So make sure you understand that's a positive number there. Now you can go ahead and calculate equivalent circuit. And I'm just showing you how to calculate the easier parameter, Y open circuit, and not Z open circuit, because you have these two elements in parallel with each other and it's harder to tease them out. Or if you're doing things from the short circuit perspective, you just have a bunch of series elements there. And now you just equate parameters. You can see my R, C, XM, showing you the process to go ahead and equate, or R equivalent and X equivalent, which again is going to have these two and these two combined together with the secondary impedances reflected over, so you can tease out those values that way. And that was it for transformers. And then we moved on to AC machines, and we really spent a lot of time using our hand, right, with a positive current going in and our fingers wrapping in the direction of the winding. Our thumb would point to the corresponding magnetic field that is produced from that current flow. So you have to have a closed loop, right? You have to come back on the other side of the machine and your thumb points in an orthogonal direction. That's part of the vector calculus part. But again, we just use our right-hand rule and we just do it orthogonally. It makes it easier. But we sum those together to see that we got a nice rotating magnetic field that had a constant magnitude. Its magnitude never varied, which is great because in an AC machine, we would like to produce a constant torque. we don't want a variable torque, at least from an industrial perspective. Maybe if you're driving a car and need to put more acceleration or less acceleration, we would go ahead and do it that way. But we went ahead and we got this beautiful magnetic field that rotated just because of current flow in the stationary set of windings. And we then evaluated by saying, let's put more windings in there. And because we don't need a balanced system, we can't just add one. You have to add 3 sets of windings, right? Because all the systems have to see the same thing. And then when we divvied those up, we saw that the motor only, the magnetic field only had to rotate another 180 degrees as opposed to 360 degrees to get to another phase A or phase B or phase C. And so what we did by doubling or tripling or quadrupling the number of windings we had, we would generate another pole pair. We would get another pole, a magnetic pole, because of those current flows. And what that allowed us to do was slow down the mechanical speed of operation. We still have electrically, we have those things spinning along at 360, well, not 360, but whatever omega works out to be. But the mechanical speed of operation gets slower. So another huge advantage, because we can change the speed of operation just by introducing more poles. Then we talked about losses in the machine, both as a motor and as a generator. You can tell it's a motor if the power coming in is electrical, right? You would have electrical power in and electrical power out if it's what's called a rotary converter, but you hardly ever see those anymore. So most of the time, if you just looked at the power coming in and it was electrical, then you know it's a motor. Generator is the opposite. The power going in is mechanical. Okay, so you don't even need to look at the output power. You can, but the concept is a motor is driving a mechanical load and a generator is generating or really converting energy to be delivered through electricity. And then you can see the different, chunks getting lost. There's some I²R losses. There's some core losses. Then we get into mechanical losses and stray losses. And all of those are the same. It doesn't matter if it's a motor or a generator, because that AC machine is exactly the same, whether it's a motor or a generator. It just depends on the power coming in. So you have all those losses. It's just, where they occur. Then we also talked about power being converted. So it depends on the application, but sometimes our power gets converted. It could be developed power or converted power. Usually converted power means, from an AC machine's perspective, it's converted from, because I can't talk, it's converted from one side, if you will, let's say it's called the primary winding, into the rotor circuit. So it's still considered electrical here, okay? Developed power is equivalent to mechanical power that you would have. Or if you had an equivalent, if you had a mechanical system, if you had a generator, then you have developed power that is equivalent to what the electrical power would be going out. So it's sort of the conversion between the two. Then we talked about synchronous generators. We didn't talk too much about synchronous motors because the vast majority of them are synchronous generators, but that's where most of the power in the world is delivered or developed from. So a synchronous generator always operates at synchronous speed. In the US, 3600, 1800, 1200, 900, et cetera, it must operate in sync with the synchronous speed of the machine, of the magnetic field. If it doesn't, then you got a problem. It's not going to last very long. So, in electrical engineering and everything, we want to go ahead and figure out a way to analyze these circuits. How do we analyze the circuits? Electrically, we come up with equivalent circuits. In all other disciplines, they come up with an equivalent too. They just might not call it an equivalent circuit. They might just do things from a different perspective. But in electrical, it's easier for us to talk about R's, L's, and C's with a source, and we can do the calculation that way. How do you determine the equivalent circuit? Same basic tests that we did for a transformer. We talked about open and short circuit for a transformer, but we also saw, when we did some homework, that we did no load and full load tests. It's the same thing that we do here, right? We do no load and full load tests, but we're doing those no load and full load tests as we're varying excitation. So when you want to calculate equivalent circuit parameters, you have to develop your open circuit characteristic and your short circuit characteristic curves. And we did a bunch of homework examples for that. This is just short circuit ratio. Like I said, I've never seen it other than that one application that we looked at this semester. But here's the calculation for that. Synchronous motor is the same as a synchronous generator. It's just electrical power in. But again, it has to operate at synchronous speed. How can you tell if a synchronous machine is operating as a motor or generator? It depends on that torque angle, that delta. If EA is leading VT angle-wise, then it is a motor, right? No, generator. If it's the other way, if VT is leading EA, then it is a motor, okay? So you're just looking at the angle. And we talked about that and expanded it too when we looked at regular systems. And we'll do this more if you take the follow-on class to this. Just looking at that power angle, you can tell a lot about the direction of power flowing into a system. If you want to start a synchronous machine, you really can't start it across the line. It can cause us real problems. If you remember in lab, I said, go ahead and have the circuit with the field winding open. And you saw how it only ran at like 1740 RPM. That's because it was running as an induction motor at that point. As soon as we flipped the switch and energized the field winding, it ran right at 1800 RPM. So that's one of the ways they used to start synchronous machines back in the day. Now they do more of a cheaper way to do it is use a pony motor. So get another motor to spin it up close to synchronous speed. Or you can also use a variable frequency drive. It just depends on, you know, what the capability is of the unit you're purchasing. So then starting a synchronous machine as an induction machine means we could introduce the topic of an induction machine. And the magnetic field constants, concepts, all of those applied. They still applied to an induction machine. The difference is that we weren't exciting the rotary part, right? It had to get energy from someplace, so we had to induce it. That's where the term induction machine comes from. We got a magnetic field on the rotor circuit because we had a magnetic field that was changing. And on the rotor circuit, we had a set of field windings, and that changing magnetic field would induce a current. Because of the fact that it's a changing magnetic field is required to induce a current, means we absolutely 100% cannot have the two spinning, meaning the rotor cannot spin at the same speed as the magnetic field that's resulting from the stator currents, okay? If it is, you're pushing it, right? So it cannot run in sync. If it runs in sync, there's no changing magnetic field and there's no current there, so it's just a hunk of iron spinning along. You don't have those two magnetic fields interacting. And because it can't operate at synchronous speed, we developed the concept of slip. What is the difference between the actual mechanical speed of operation and the synchronous speed? And so we've defined those here as our slip is just what the actual speed of operation is, the difference between the two, divided by the synchronous. So it's kind of a ratio, right? Like what it's essentially what the difference is operating at. Slip for a induction motor is always going to be between 0 and 1. 1 means it's fully slipped, means it's not running at all. 0 means it's running at synchronous speed, okay? And because you had a rotating magnetic field that was induced from the stator currents, you generated an AC waveform on the rotor. And the frequency of that rotor, you could determine based on the slip and the applied electrical frequency. And that had to be AC because your rotor field always has to operate in sync or at the same speed as your synchronous field or your stator field, because again, you want that constant torque. So the fact that you got something rotating with an AC waveform on it means you can get those to spin at the right speed. We spent a lot of time looking at torque versus speed characteristics, tons and tons of time there. So we built some MATLAB scripts and we built them, right? We actually created them. And all we did was circuit analysis. Once we had the equivalent circuit of an induction motor, and you'll notice, right, we didn't have, I mean, we can do some tests. We'll talk about those in a minute, but we built torque versus speed characteristics, just plotting point after point after point. That's one way if you're trying to get some input, you can just go ahead and build your torque versus speed curve. Or if you want to get some specific parameters like pull-out torque or starting torque, you can make some adjustments, if you will, or you can get some Thevenin equivalents, and you can do those calculations that way. It's just that you have to make some assumptions and simplify things down to do it, but you can do it that way. We realize that because on our rotor circuit, the most efficient we could get is when there's almost no current flowing in the rotor circuit. Then that means there's almost no current flowing in the stator circuit. So that has the least amount of losses. So operating it at the highest slip possible, almost at synchronous speed, is going to result in the most efficient application. And then we went into induction motor equivalent circuits. So we did more tests here, right? Instead of calling them no load and full load or open and short circuit, we call them locked rotor and block rotor tests. And so you could measure some data, and you can pull out whatever values you needed. So the locked rotor or block rotor tests, you can calculate X of M. And the other tests, you can calculate those. And then we had to have those characteristics of, is it a NEMA design A, B, and C, to just go ahead and tease out those values. Once you have that, I just included in here, and this should be R2 over S, not R1. I thought I corrected it here. I corrected in the other one, but I didn't correct it here. But the R2 over S here, this is just doing loop equations inside to get your values there. And then we have power flow in an AC machine. We're only doing an induction motor, not an induction generator. They do exist, but they're more complicated, and it's very unlikely that you'll ever see one. Again, unless you're working on wind turbines where they use them more extensively to operate as generators. But for the most part, if you ever come across them, it's as an induction motor. And then here are all the power calculations, even showing you this sort of ratio of how much power is lost versus how much power is converted. This is all those equations, right? So there's a lot of equations here. I won't go through them all detail. This is just some derivations, but you can take a look and see what the derivations are. And here are our locked and block rotor testing to go ahead and do that. And then starting a motor, an induction motor, you can flip the switch if you want. If your system can handle it. If your system can't handle it, then you got to use either a reduced voltage starter, which is pretty cheap and easy to implement, but it delays when that motor is fully up to speed. And then you can also use a variable frequency drive as an option. So test questions, power, right? Big topic, really important. Tell me the pieces and parts of a synchronous machine to make it work. If I give you some simple nameplate data, you should be able to tell me some transformer operating information, voltages, currents, that type of stuff, maybe turns ratio. If I give you magnetic fields, I mean, I said determine magnetic fields based on stator configuration and currents, so using your hands to get the directions. Phasor diagram, tell me if it's a motor or a generator, if it's producing reactive power, if it's absorbing reactive power, that type of stuff. And then calculate some parameters, speeds, output, that type of stuff for an induction motor. Questions? We covered a lot of material over the semester. Everybody know when the test is? It's going to be in this room a week from today, 8 to 10. Remember, don't complain about the time of the day. I have nothing to do with it. That's what student records determine you all get. So you get 4 sheets of paper, right? We talked about that. It's comprehensive. Yep. You can get both sides. I don't imagine you'll need it, but if you want it, it's up to you. There won't be anything that we included because we only had one class on power electronics, and we would need more time to really delve into that. So, feeling good? Ready? Got a week, so. How about TV Land? You have any questions?
Nothing here.
Okay. Well, that's all I had. It's your exam review. If you feel comfortable, we'll call it a class. Have a great day, everyone. Enjoy the nice
Hey,
weather.
Paul, one quick question.
Yes.
Based on like if I go to the Brightspace page for the grading, the way that's broken out, is that the weighting of this? So the exam is 20%, and then if you look back at the other points, it kind of dictates the weight of each of our grades?
Yes, so it should coincide with what was in the syllabus, but each exam is 15%, the final is 20%. And I can't remember homework and labs, but that is also spelled out in more detail. But if you take a look in Brightspace, it should jive. That's how I set it up. So your points are delivered or determined based on that.
Okay, yeah, that matches with what I just looked at. Thank you.
Okay. Yeah, and I can't share that because I would share people's grades and I'd get into a lot of trouble. So normally I would bring that up and show you, but can't do that for hopefully obvious reasons.
Yep, that answers my question. Thanks.
All right, thanks, Joe. Anything else? Okay, have a great day. See you next Thursday. Take care, everyone.